This video is about graphs of logarithmic functions and how they are related to graphs of exponential functions. For example, we do know that exponentials and logarithms are actually inverse functions of each other, which means something very precise for the graphs. So let me remind you guys how the graph of, for example, y equals 2 to the x, an exponential with base 2, looks like. So if we recall, it crosses through 0, 1, and it increases, and it has a horizontal asymptote at x equals 0. Now, what does it mean for graph of a logarithmic function, for example, log of base 2? Well, if we know that the graphs are inverses of one another, what we do know is we can switch x and y values, and that's basically how we obtain the graph. So the table we have seen with the x and y values, we can simply switch them to figure out how to graph the logarithmic function. So let me center it a little bit. So everything switches, including we knew how there was a horizontal asymptote. Now we have a vertical asymptote at x equals 0. And also the y-intercept that was 0, 1 became x-intercept at 1, 0 for the logarithm. And notice how it's sort of slowly going to infinity. And what we do know about the logarithm is there are several things. First of all, the domain is actually from 0 to infinity, or all positive numbers, just for the logarithm of y equals log base 2 of x. So for any base that's bigger than 1, we know that the graph would look like this. It will be slowly increasing. The domain is all positive numbers. Actually, it starts with the asymptote, 0, so we know it cannot cross the asymptote. The range is all real numbers. And the logarithm is slowly increasing to infinity. So logarithms have a much slower growth rate than exponentials, for example. So as we know about the inverse functions, this is actually a reflection of the exponential, except it's a sideways reflection, or a reflection about y equals x, for example. So if we know there is an exponential, we can reflect it and we'll get the graph of the logarithm. And let's take a look at the general graph. There you go. Any graph of a logarithm of a base bigger than 1 looks very similar. It passes through 1, 0. This is a key point that we know. And it has a vertical asymptote. Now be very careful. If you're using graphing calculators to graph, for example, y equals log of x, which basically means base 10 right here. So actually I will add it to here. If you use a graphing calculator, then the graph would look something like this. The general shape is correct, but be careful. The graphing calculator, first of all, does not account for the asymptote as we see right here. And even though it looks like the graph touches the y-axis, it cannot actually touch. In fact, it continues and it gets as close as it can. But graphing calculator cannot account. In fact, I think for some shifts, it looks something like this, like it stops. It looks more like a radical equation than a logarithm. So we do know it does continue for whatever the asymptote may be. So we have to account for that behavior. So let us also take a look at, now notice these are characteristics: the domain, the range, the x-intercept, the y-intercept, which there are none, and the vertical asymptote, which is x equals 0. What else do we know? What about the basis that's between 0 and 1, which is the decay situation? So if we recall the graph of 1/2 to the power of x, which looks like this, it's a decreasing function. Let's take a look and see what it does to the logarithm. If we do the same thing, if we switch x and y and we plot these x and y along, it also looks like a decreasing function. So it's very similar. It has the same asymptote at x equals to 0. It has the same intercept, but it's actually a decreasing graph as opposed to increasing. And any graph for y equals log of a of x for the base between 0 and 1 would look the same way. Now, we can actually apply shifts to be able to sketch graphs fairly easily without necessarily using graphing calculators. What about something like log base 2 of x minus 1? Well, there are a few things we know. If we can recognize this is actually a shift, a horizontal shift, because it's together with the x, it's actually in the argument. And if we recall something about shifts, we know it's shift 1 to the right. So minus 1 means to the right. How else we can check it? Well, we know for the domain that x minus 1 has to be greater than 0 for the domain of the logarithm, which means x has to be greater than 1. Well, this 1 value is our new asymptote, and that's how we know that the shift is 1 to the right. So how does a graph look like? Let's take a look. There you go. The whole graph, so now the asymptote shifted from x equals 0 to x equals 1. The intercept, which was previously at 1, 0, is now at 2, 0. So this is how the horizontal shift looks like. What about if we have a couple of shifts? Let's take a look at the next example. Negative 5 plus log base 3 of x minus 1. Once again, the base is bigger than 1, which means the basic graph looks something like this for this shape. But what would be the shifts? Well, we do know the negative 5 now. There is a number that's added outside of the function. That corresponds to the vertical shift. In fact, it would be shift down because of the negative 5. Now the minus 1 right here is very similar to this logarithm. It would be shift 1 to the right again. So how does a shift down account for the graph? Well, notice it's very similar shift 1 to the right with the asymptote. Now the asymptote cannot shift up and down because it's infinite, so it stays in the same place. But the point that used to be at 2, 0 now is at 2, negative 5. So the point went from here, went 1 point to the right and 5 points down. And this is the new point that we know. The general shape is the same, even though the base is different, but the shape is the same, and this is how the sketch looks like. Let's take a look at one more example. How about 1 plus log base 2 of x plus 4? Well, as we can guess, now the shifts would be 1 up, because of this value. It's positive now, so it's up, and 4 to the left. And again, it's to the left because it's plus right here. So as we can see. So how does the graph look like? Well, because of shift of 4 to the left, the asymptote, and I usually graph it first, is now at negative 4. Now the intercept, which was at 1, 0, is now shifted 4 units to the left, 1, 2, 3, 4, it's at negative 3, and also 1 unit up. And so here is our new point. And we have a sketch of the graph from here.